So exam number 3 from spring 2018. Problem number 1 is a uniform steel disc rotating about a vertical axis, so you can imagine the axis coming out of the page towards you. Okay, you're given the radius of the disc, you're given the mass, you say it's uniform, so that should immediately tell you it has a moment of inertia, I equals 1/2 mr squared. That's on the formula sheet. It's initially at rest. You apply a force here at an angle with respect to a tangent to the edge of the rim. That angle is 60 degrees, and that makes this disc spin counterclockwise. That's a sense of the spin. That's not a direction of an angular velocity, remember. That angular velocity, by the right-hand rule, is coming out of the page towards you, because you curl your fingers of your right hand in this sense. Okay. And after 10 seconds, and by the way, it's a constant force, so a constant torque, so a constant angular acceleration. After 10 seconds, you've got the frequency that it's spinning at, you've got the time after 10 seconds, and you start by asking, what are the magnitude and direction of the angular velocity vector, final angular velocity vector? So this was meant to be a simple question just to get you started, because you should know the connection between angular speed, okay, or velocity, and the frequency of motion is just omega equals 2 pi f, and of course that's on the formula sheet. So it's just 2 pi, and you're given the f is just 5 revolutions per second. And remember, revolutions doesn't actually have units, so we'll just ignore that, but I'll write it in there to help you follow. So the answer is 10 pi radians per second. Okay, so I can write, and I can multiply that out if we want. And you should, if you're given numbers and you're asked for a number, you really shouldn't include constants, pi's and speed of lights and things in it. And so it's appropriate to do that multiplication, 3.14 radians per second. And actually, units are just per second. Okay, but sometimes I'll carry along that. For this problem, we'll accept it with or without the pi, although it's probably better to put the substitute for pi 3.14. Now the direction is from a right-hand rule. And I already showed you how that worked. Okay, the direction, right-hand rule is this. But what is that direction? If this is x and y, you know that you know the right-handed coordinate system. The problem tells you positive z points out of the board because x cross y has to equal z. And so the direction of the rotation is in that same direction. So that's plus z hat. So that's the first part, part A of problem number 1. Part B asks you for the magnitude and direction of the angular acceleration vector. Well, angular acceleration instantaneously is just d omega dt. I'll leave out the vector signs for a moment and treat that separately. Since it's a constant acceleration, we can place the derivative by a delta omega over delta t, because it's constant acceleration, angular acceleration. So the angular acceleration magnitude, or omega, is just delta omega, omega final, minus omega naught, divided by delta t, which is 31.4 inverse seconds from above, because that's the final omega. The initial omega naught was 0. It started from rest, divided by 10 seconds. So we're back to 3.14. Units are radians per second squared, or if you like, just per second squared. Or if you didn't take the pi out there, you probably didn't do it here either. So pi radians per second squared, or just per second squared. So that's the answer, part of the answer to B. Now the next question, or part of this question, is what's the direction of alpha? So let me just draw a side view of the system. This is z hat. And so in the z hat direction, okay, which is looking out of the page actually, omega is getting bigger. It starts at rest, so omega final is getting bigger. Omega naught is 0. There is no vector. Delta omega is this minus this, or it's something that's also in the z hat direction. So the direction of delta omega, put the vector sign back there if you want, will also be in the plus z hat direction, because omega is in the plus z hat direction and growing larger. So that's the other half to the answer of part B. Now part C was probably a bit more challenging. It asks you what's the torque. Okay, that's or I'm sorry, it asks you what's the magnitude of the force F that provides the torque that gets the disk spinning. And here to answer this question, you have to be able to think in torque in a couple of ways. Now let's just worry about the magnitude of the torque to start with. Okay, the general definition for torque is R cross F, and you have various ways of thinking about it. Let me do this in terms of RF sine theta. But we also know, since we don't know F, we also know that the torque is what causes angular acceleration, and that relationship is I alpha. Just like MA, but for rotational motion, the torque will also give you I alpha. And so it's this connection, I alpha equals RF sine theta, that will let us solve the problem. Now, before I go any further, let's worry about the sine theta. So here's a tangent to the disk, and I gave you an angle of 60 degrees for the F relative to the disk. But that's not the angle that is going to go into sine theta. Remember, this requires you move R and F tail to tail. So this is F. Let me move the R vector, which goes from the axis out to there. Let me just shift it here. We're allowed to shift vectors. And what you should see is, the angle we want for sine theta is actually 30 degrees. So that's the angle I'll be using in my calculation. So now let's go solve this expression for F. F will be I alpha over R sine theta. The moment of inertia of a uniform disk is 1/2 mr squared. That's on the formula sheet if you don't know it. Times alpha divided by R sine theta. I can divide out a factor of R and simplify this, and so the force magnitude will be mr alpha over 2 sine theta, and we know all those values. All I have to do is plug them in and say the force is 2.00 kilograms because that's the mass of the disk. The radius of the disk is 1.50 meters. The angular acceleration, alpha, is 3.14 per second, or squared, radians per second squared if you want, divided by 2 sine 30 degrees. Pull out your handy calculator. Okay, plug in the numbers, and you'll see the answer for the force, the magnitude of the force, is 9.42 newtons, or if you keep the pi along for the ride, 3 pi newtons. So that's the magnitude of the force. Okay, that's all we need in this case, just the magnitude. By the way, the direction of the torque due to that would be R cross F if you cared. So it would be R pointing out from the center to where the force is applied, cross the direction of the force is like this, and come out of the board. So the torque, direction, and alpha align as they must. Okay, that brings us to D. Part D asks you how many rotations does the disk make before it reaches full speed. Well, this is a basic kinematics question, like asking if something's accelerating translationally with A, okay, over a certain time t, how far does it move? So in this case, though, we're asked for the angle it rotates through, how many rotations, so theta minus theta naught, where theta just stands for theta final. That's equal to 1/2 omega naught plus omega times t. Now, there are other ways to get this. They'd be a little bit clumsier, I think, using those 4 handy-dandy equations for angular motion with constant acceleration, just like the 4 equations for translational motion with constant translational acceleration. But this will be the quickest way to get there, even though you have other options, because this just gives us directly the change in theta is 1/2. Omega naught is 0. It starts at rest, ends up at 10 pi radians per second. I'll keep the pi in there just for the heck of it, times 10 seconds. So you've got 50 pi radians, or 50 pi radians of rotation, or plug in the pi and you'll have 157, okay, radians. Okay, and it did, well, that's radians. The question asks you for rotations. So rotations, to make that conversion, you do delta theta, and you say, well, I've got 2 pi radians per rotation, 50 pi. Now you can see why I kept the pi and divided by 2 pi is just 25 rotations. So the wheel spins around 25 times in these 10 seconds. Okay, that takes us to the last part, which is actually tests a different concept. After the disk reaches full speed, okay, you remove the force, but you drop a magnet, or a magnet of mass m, vertically onto the disk. What's the angular speed now? And so you should recognize that, first of all, you can't use forces and torques for this because you have no idea the forces between the magnet and the disk while it's coming up to speed. But when you drop the magnet vertically, it has no angular momentum. Okay, it just falls vertically, so there's no angular momentum in the sense that the disk does. And so there are no external torques acting on the disk when the magnet touches it. And so angular momentum is conserved. So this is the key concept, is conserved. No external torques, okay, during this process. So angular momentum, so we can say that L final equals L initial, okay? L, of course, with L equals I omega. So we need to get the initial angular moment of inertia. Well, that's just the moment of inertia of the disk, 1/2 mr squared. The final moment of inertia is the disk 1/2 mr squared plus a point mass at the edge of the disk, which is plus 1/2 little m. Okay, r squared. It's also at the edge of the disk. So now we can just write out, oh, okay, L final equals L initial, so I final omega final equals I naught omega naught. Solve this for omega final. Omega final equals I naught omega naught over I final, with I naught equal 1/2 m r squared. I final 1/2 m r squared plus little m r squared, all times omega naught. Okay, so solving, well, simplifying this, first of all, let's just divide out all the r squareds. We don't need them anymore. So omega final is just equal to capital M over 2 divided by capital M, the mass of the disk, over 2 plus little m. Plug in the values. The disk has a mass of 2.0 kilograms, so half of that is 1.00 kilograms divided by 1.00 kilograms plus the mass of the magnet, and the mass of the magnet is 0.25 kilograms, all multiplied by omega naught, which is 10 pi. And we're almost done. Just do the math, and you find that omega final equals 8 pi radians per second, and you can leave out the radians if you want and just say per second, or equal to, put in the pi, 25.1. I'll just do per second for this case. And we're done with problem number 1.